All right, our second topic that we're going to look at today, we did power rule in the first lesson on derivatives, so let's just quickly refresh that. So if I gave you a question like y equals 4x squared minus square root of x plus 1 over x, even though these are all different powers, we can still use the power rule. If we rewrite the question as 4x squared minus x to the half plus x to the negative 1. Now they're all just single powers, so our derivative was pretty simple. Bring the 2 down, so we'd have 8x. For the second one, bring the half down, drop it to negative a half. And for the last one, bring the negative 1 down, drop it to negative 2. So remember, the power rule works by bringing the power down in front, dropping your power by 1, and then do each term individually. Everything is good. So what we're going to look at, and we can't turn them into individual powers. So we're going to look at what we call the product rule and quotient rule, which you can probably guess. The product rule is when we're multiplying things. Quotient rule is when we're dividing. So the power rule works by itself or for adding or subtracting, but nothing. So let's start with the product rule. And what happens is we still use the power rule, but we have to sort of set it up slightly differently. So when we have a product rule, what we're going to be looking at is things that have two different functions being multiplied. So for example, if I gave you a question that was y equals 3x squared times, say, 6x, obviously we could still do this one as a power rule. So let me just quickly do that. So if we combine them into 18x cubed, our derivative now would be 18 times 3, which is 54x squared. So we already know we could do this one as a power rule, but let's try it as a product rule just to see if we get the same thing. So the way the product rule works is we have two separate functions. So we're going to call one of them f and one of them g. Letters don't matter, but I'm just going to match it to this formula. So what happens is we got to do the derivative of each. So I'll just write below here. Our derivative of f then is 6x. Derivative of g is 6. We don't multiply those two derivatives. We have to multiply them with the opposite original. So if you look at the formula, it says g times f prime. So we're going to multiply 6x times 6x. So I'll kind of write it above here. So g is 6x. F prime was also 6x. And now we add the other two. It's 3x squared times 6. So we just got to be careful when we do the derivative of each, but you got to kind of cross multiply in a way, right? We're kind of doing the diagonal two things multiplied together and then added. So when we do that, we would get 36x squared for the first one, 18x squared for the second one, which we could combine into 54x squared. So you can see we do get the exact same answer, it's just a different approach. So do we need to use the product rule? No, we want to use the product rule when it's not a practical way of foiling things out. This question that we just did, it'd be a lot easier just to multiply it and do the power rule by itself. But as the questions get harder, the product rule will come in more and more handy as we go. So the formula I circled was the FG prime one. That's just using the prime notation. The other formula I have on the bottom is just the same thing, but using the dy dx version. So if you have two functions, in this case, let's call them u and v. So our derivative would be v times the derivative of u plus u times the derivative of v. So it's the same formula, just kind of written slightly different. Most people like the stick with. So here's a couple examples. Let's go through these fairly quick. So if we call our first one f, second one g, derivative of f is going to be 14x to the 6. And our derivative of g is negative 21/5 x to the negative 4. So you can see the derivative of each are pretty easy. Let's kind of crisscross them. So let me write out the derivative. So we'd have 7/5 x to the negative 3. That's our g. We're going to times that by 14x to the 6. And then add the other two. So the other two would be 2x to the 7 times negative 21/5 x to the negative 4. And then all we do with the product rule is simplify, common factor, put like terms together, all the same sort of algebra stuff that you've done over the years. So for this first one, if we multiply 7/5 times 14, that gives us what's 7 times 14? That gives us 98 fifths. And then if we add our powers, that's x cubed. For the second one, we'd have minus 42 fifths. X cubed again if we add the powers. So 98 take away 42 would be 56 fifths. Okay, so you can see product rule works fine. A little bit extra work. Again, probably with this one, it would have been simpler just multiply them right off the start. Make it 14 fifths x to the fourth, and then we could have got that answer just by doing the power rule. But let's practice the product rule, because like I said, this becomes more and more important later on. So once you understand the process, it'll make things a lot easier. Okay, let's do the one below it here. So we'll do the same thing. If f is x cubed, f prime would be 3x squared. And let's do the same thing for the second one. G will be x squared plus 2x. So g prime would be 2x plus 2. So now let's do our multiplying. So let's multiply those two first. So 3x squared times x squared plus 2x plus the other two, x cubed times 2x plus 2. And let's simplify all that out as much as we can. So if we FOIL the first one, you get 3x to the fourth plus 6x cubed. And the last one would be 2x to the fourth plus 2x cubed. That was a plus. Okay, and you can see we got a couple like terms again. Put our fourths together would give us 5x to the fourth. And put our cubes together, we would have 8x cubed. And that's it. So you can see it works pretty straightforward. Just do the derivative of each, do your cross multiplying, FOIL, and simplify as much as you can. Okay, maybe we'll do one more. We'll leave the last one. This bottom one would be almost the same, just a little bit longer, but it would work the exact same. So let's try this last one. So if this is our f, our derivative would be 20x cubed. And if we call that one our g, remember we'd write it as x to the half. So in this case, our derivative would be 1/2 x to the negative a half. So let's write out our multiplied step. So we'd multiply those two first. So we'd have x to the half times 20x cubed. And then the second part would be 5x to the fourth times 1/2 x to the negative 1/2. So let's simplify that a little bit. We would get 20x to the 7/2 if we add those two fractions together. Oops, let's fix that a little bit. So 20x to the 7/2, and then the top would be, or the second one would be 5/2 x to the 7/2 again. And in this case, we can just add the 20 and 5/2 together, which would be 22.5 if we leave it like that, or we could write it as 45/2 if it was a mixed fraction. It doesn't really matter. So when you're simplifying these, whether they're mixed fractions, decimals, any method is totally fine. Product rule. Let's take a look at the quotient rule. So now, quotient rule obviously is going to be when things are being divided. And if you kind of follow what we just did, multiplying, we added the two combinations together. Quotient rule, we're going to subtract. The difference between the formula, you can see because we're subtracting, order matters. So we got to make sure we get the terms in the right order. But we also get an extra thing on the bottom where it's the original bottom g function squared. Okay, so let's kind of first of all look at why it would be squared. So if I gave you a pretty basic equation that looked like 1 over x squared, we wouldn't need to do the quotient rule with this one. We could just rewrite it as x to the negative 2. So if we do that, and we just do our regular derivative, we would have negative 2x to the negative 3, and we'd be done. Okay, so now let's try this same question using the quotient rule. So let's call the top 1. So that derivative would be 0. Let's call the bottom x squared. So that derivative would be 2x. So now if we plug it into the formula, we would multiply these two first, so 0 times x squared, which is just 0. Take away the other two, 1 times 2x, all over the bottom squared. So it would be all over x squared squared. So you can see when we simplify the top, 0 times x squared is 0, so we get minus 2x and over x to the fourth. So you can see if we cancel out an x on the top and 1 on the bottom, we'd get negative 2 over x cubed. And you can see that answer matches exactly what we did with the power rule. So what happens, and the reason why we get this squared on the bottom is, with the power rule we have to drop a power, but when they're negatives, that negative gets bigger, right? So the x squared on the bottom turned to x cubed, and then x to the fourth, sorry, and then we canceled one of them out, which left us with x cubed. So it's sort of a part ways between fractions and common denominators is what makes that bottom bigger, or you can think of it as just being a negative power. Because it's a negative number, the number itself gets bigger instead of smaller. But in either case, it's not a really big deal if you don't really understand why it works. We just have to use this new formula. And then the bottom formula is the same thing, but just using dy dx notation instead of the prime notation. Let's look at a couple examples with the quotient rule, and you can see it works pretty much the same. The problem with these ones is we can no longer use the power rule, right? As soon as the bottom has more than one term, we're forced to use the quotient rule. So the quotient rule is going to be used quite a bit more than the product rule because there is no other option. So in this case, if we call the top our x cubed, our derivative would be 39x to this 2. And if our bottom is 5x minus 1, our derivative is 5. So when we use our formula, again, the order matters this time. So we have to start with the two diagonals that I just highlighted in blue. So let's multiply those together first. So 39x squared times 5x minus 1. And then we subtract the other two. So 5 times 13x cubed. The order we write those two multiplying doesn't matter, just the subtraction order matters. And that would be all over the bottom squared. So just like we did with the product rule, our only last thing is let's simplify the top as much as we can. So 39x squared times 5, that gives us 195x cubed. Take away 39x squared, if we FOIL that out. Multiply the other two, gives us 65x cubed. The bottom stays the same. And all we can do is simplify the top a little bit. Let's go 195 minus 65, which would give us 130 x cubed minus 39x squared. And we can stop there. That's pretty good. But sometimes you can common factor a little bit. And I can see on the top here, we could take out a 13 and we could take out an x squared on both. So I think the best way to write this one would be 13x squared times 10x minus 3. And then our bottom still stays the same. Don't FOIL out the bottom. You don't need to simplify that. It'll always work just the way it is. Once you square it, just leave it as is. So that would be the final answer for that first question using the product rule, or quotient rule. All right. So let's do one more with quotient rule. So looks a little bit different, but it's still the same process. Do your top term, do the derivative of the top, which is 2x, do the bottom term, and that derivative would be 2x plus 2. Do our FOILing out, and again, remember you want to start with those two as our starting location. So let's go 2x times x squared plus 2x minus 3. Subtract the other two. All over our original bottom thing squared. And the bottom won't change. We don't need to factor or do anything FOILing out or nothing. Just leave it exactly the way it was, squared. Okay, so it looks something like that. So just like we did with the first one, the only thing we can do is simplify the top. So we need to FOIL out all this stuff on the top. So I'll rewrite it here. We're going to have 2x cubed plus 4x squared minus 6x. And the second part, let's keep that in brackets for the time being, and then we'd have subtract all of the second one, so let's FOIL that one out. So we'd have 2x cubed plus 2x squared plus 2x plus 2. And the bottom stays the same. I won't even write it yet because it doesn't really matter. So we just simplify the top, so you can see the 2x cubes would cancel. We have 4x squared minus 2x squared, which would give us 2x squared. Negative 6x take away 2x, which would be negative 8x. And minus 2 is our last term, all over our bottom squared still. And in this case, we could pull out a 2 if we want to pull out a common factor. So let's do that. So we'd have 2x squared minus 4x minus 1 all over our original denominator squared. And that would be our final answer for that one. Okay, so you can see a little bit messy in terms of the simplifying, but again, the process should be pretty straightforward. Do the derivative of each, plug it into the formula. In this case, remember we're doing g times f prime, take away f times g prime divided by g squared. So that's the formula we're using for quotient rule. You'll get it on your formula sheet, but it's good to sort of have it memorized as well. Okay, I have one more on here. So again, could we use the quotient rule for this question? We could. We see its division and it would totally work, but we can actually make it a little bit easier. You can see we have just one term on the bottom, so we can actually change this to a power rule question. So I wouldn't do quotient rule for this one. It would work still, but it'd take you a little bit longer. I would just think of this as being a simple power rule question if we divide out both terms by 2x to the 5. So if we do that, we get 7/2 x to the negative 3 for the first one, and we would have negative 3/2 x to the negative 4 for the second one. Now our derivative is pretty straightforward. Bring the 3 down, so we'd have negative 21/2 x to the negative 4, and for the second one we'd have plus 12/2 or 6 x to the negative 5. So it works good. If you were to do this as a quotient rule question, what it would probably end up looking like is you would end up getting an answer that would look slightly different, but it would still be the same thing. You'd probably have something like negative 21x plus 12 over 2x to the 5. Right? That's what I'm thinking it would simplify to. So you can see it's similar to our original question, but the bottom would have been 4x to the 10 when we squared it, but that would have probably canceled out or simplified or whatever. So this answer, to get it kind of comparable, the power rule is what we got here. As a quotient rule, it would have looked something like that, but you can see they would have given us the exact same answer in the end either way. Okay, one more. So if you look at this last one, this one we have to do quotient rule. There is no other option. But what we can do is we can simplify it first. So it is worth our time to see if we can make it a little bit easier. If we change the top to just 7x to the half, and if we factor out an x on the bottom, okay, it doesn't change the question, but it'll actually make things a little bit easier because we can combine the x's. So what I would do with this one before we start the quotient rule is we could change it to the 7 would stay the same, but if we go x to the half, take away the x on the bottom, or kind of cancel it out, we could actually just rewrite it like this: x to the half on the bottom, and then x minus 4 by itself. Okay, so that would work well. Actually, now that I look at this, it might be even better to make it a product rule. So let's rewrite it one more time. Let's bring the x to the half to the top instead, which we could have got right from the original. A half take away 1 would have been negative a half. And let's bring that x minus 4 to the top and write it as negative 1. No, that doesn't work. That's not such a good idea. We haven't figured out how to deal with those brackets yet. So let's leave it. We'll kind of get rid of that last step. Let's change it back to just 7x to the negative half on the top, but let's leave it as x minus 4 on the bottom. And that should work well as a quotient rule. So let's try it. we call f 7x to the negative half. That derivative would be negative 7 halves x to the negative 3 halves. And our bottom is x minus 4. That derivative is just 1. So that works nice. Do our quotient rule. Start with those two. So negative 7 halves x to the negative 3 halves times x minus 4. Take away the other two, which is just the 7x to the negative half, all over our bottom squared. And if we FOIL out the top, let's do that step. So we'd have negative 7 halves x to the negative 1 half, because the negative 3 halves plus the 1 would give us 1 half, negative a half. And then FOIL out the second part would give us plus 14 x to the negative 3 halves minus 7x to the negative a half, all over our bottom squared still. So our first and last terms we could put together, so that would give us, I'll rewrite it up here, so that would give us negative 21 halves x to the negative a half plus 14 x to the 3 halves, negative 3 halves, all over the bottom squared still. So we could probably stop there, that would be acceptable, but let's keep going one more step. Let's try to common factor the top. It's good to kind of get rid of these fractions. So if we take out a 7 halves, I think will work. Like out of the 21 and 14, the lowest common denominator, or lowest common factor would be 7. But because we have fractions, let's take out the half as well. Let's also take out the smallest exponent, which would be negative 3 halves. And then let's see what's left over. So 21 halves divided by 7 halves would give us 3, or negative 3. Negative a half subtract negative 3 halves would give us positive 1. So that should just give us negative 3x. And then for our last term, 14 divided by 7 halves gives us 49, I think. Let me just double check that. 14 divided by 3.5. Oh, it's only 4, sorry. Yeah, 14 divided by 7 is 2. Times 2 would give us 4. So that makes it nice. And then our bottom stays the same. And we're done. So that would be our final derivative for that one. So again, if we would have done this slightly differently, like maybe we left the original the way it was, your answer might look a little different, but after you simplify it, it should look exactly the same as what we just calculated. So that's it. So that's where we'll stop with the product and quotient rule. Our next topic is the chain rule, and this one is kind of like I originally had, where we would bring this bottom thing to the top and write it in a bracket to the power of negative 1. Once we understand the chain rule, that would have been a good strategy for this question as well. So we'll stop there and we'll pick it up in the next lesson.